Boa tarde a todos. A próxima apresentação é do professor Shrek Zhang. Professor Zhang received his bachelor in biomedical engineering from the Southwest University in China in 2008, and he mastered in biomedical engineering from Washington University in St. Louis in 2011, and his PhD in biomedical engineering at Georgia Institute of Technology in 2013. Dr. Zhang is currently an assistant professor in the Department of Medicine at Harvard Medical School and associate bioengineering in the Division of Engineering in Medicine at the Brigham and Women's Hospital. Dr. Zhang is directing the Laboratory of Engineering Living Systems, where the research is focused on innovating biomedical engineering technologies, including 3D bioprinting, organs on a chip, microfluidics, and bioanalysis to recreate functional tissues and their biomimetic models for medicine. He is author of 2045 peer-reviewed publication, H. Index 67, and his scientific contribution has been organized by more than 40 international, national, and regional awards. Hi, Shrek. Thank you for your contribution. You have 25 to 30 minutes to your presentation. Thank you very much for your cooperation.
All right, thanks so much for the invitation. Let me see if the slide is working as well. All right, so yeah, thanks again. So yes, today I'm going to talk about some of the things that we have been doing the past few years on how to use biofabrication for emulating tissues and organs of humans in vitro. So a little background to start with. So we have been really interested in many different types of technologies and primarily focused on two threats. First one is basically tissue model engineering, basically engineering of these human tissues and organs in vitro. Rationale for that is conventionally used models based on, for example, two-dimensional static cell cultures, or these animals don't really translate in the human system, right? Meaning that if you test drug that's positive in these models, they don't really behave the same way in the human system. So that's why a lot of things actually fail during this drug development process. So that's why in the past 10, 15 years, people have been really trying to develop these so-called organ chip devices, high content models of human tissues and organs to allow better drug screening. So not only can you have these individual organs, but you can also link these organs in a way that human tissues and organs are linked together in our body. So you can start to also look at the interactions and also like multi-tissue, drug interactions in vitro as well. So then with those in mind, you can start to really develop drugs in a better way. And also if you link these devices with cells that are coming from different patients or donors, then you can start to also process medicine, basically screening therapeutics according to the different patients' kind of characteristics. All right, so then, but also you can imagine these same technologies can be extended to like the conventional tissue engineering applications, right? Basically, fabrication of this human tissues and organs that are functional that can be put back in human system for replacing those tissues and organs that are damaged or diseased. But this is a longer term goal because, I mean, in this case or scenario, we have to make sure that everything is entirely functional before we put them back in human system, whereas in the other case, tissue model engineering, you can you don't have to really make them 100% functional in most cases. All right, so then with all those backgrounds we have been discussing, our lab has been really interesting, like a range of different technologies that can allow us to fabricate tissues in different ways, right? So this can range from biomaterials to biomaterials engineering to biofabrication, especially bioprinting, and all the way to biomedical devices like this on-chip devices, and all the way to like bioanalysis. For example, one of the things that we have been really trying to do is to combine these different technologies like the biofabrication and like on-chip devices to allow better emulation of human tissues and organs in vitro and for different applications. So I'm going to give some examples of each of the categories here today to really discuss how we have been able to using this technology to really develop tissues and the organs that are potentially functional. So here are some examples of the on-chip devices, right? Basically, magnetic chip devices. So this can be made of different complexity or different configurations. For example, you can have a little single chamber in the middle that's hosting the organs or tissues in there. You can have multiple chambers built into single chips. You can now start to look at their interactions, I mean, the different like cell type interactions on the same chip. You can also build in all these dynamic cues in there, right? So not only flows, but also these mechanical kind of actuations to model some of the tissues that are sort of mechanically active in human system, like the vessels or the other tissues. As mentioned, you can also start to really link these different tissues together in a way that they are connected in the human system, right? So then you can start to do all the multi-organ sort of configurations on the same devices for those kind of interactions. So more specifically, as mentioned, right, so you can have all these kind of chips linked together in a way that the different organs are linked together in the human system. So we actually did this through a device called breadboard, which has all these on-chip valves that are controlling the flow of the liquids into different modules at different time points, right? So, for example, in the movie shown on the right, you can see that these two the compartments are actually continuously perfused. And the third module here is actually isolated completely until when you open these valves. And now you can see actually the flow of the liquid into the third module, right? So again, everything is tightly controlled on the chip. You can really determine when the liquid is going, going to which module at the in a very precisely defined way. And you can also expand this complexity to a pretty high complexity. Here shows a chip that's having over 30 different channels in there, and everything you see here is basically automatically programmed. All right, so then some concrete examples on how they can be used. For example, you can have a little chamber, but then in between the chambers, you can have a membrane that's becoming endothelialized. You can now start to really make a little compartmentalized device having endothelial barrier to model the vasculature, right? So if you look at the proliferation, the cells are proliferating on top pretty nicely. And if you look at the resistance, right, so basically electricity properties over there, you can also see the growth of the resistance, meaning that the cells are forming tighter and tighter junctions as they grow into confluency. So this vascular barriers are actually functional as well if you do a simple dye diffusion assay. If you put this dye molecule in the bottom layer and look at how it's diffused into this barrier, if there's no confluent barrier, of course, you can see very fast diffusion of the molecule through this endothelial kind of configuration. But if you have a tight barrier, confluent barrier, then you see much slower diffusion of the same dye molecule, meaning that the barrier is actually functional, right? But then if you at some point infuse this histamine molecule, which is known to be a vasodilator, you can start to increase your the permeability of the vasculature, right? So you can see increasing trend of the diffusion from this point on, meaning that the barriers are not only functional, they're also responding to these molecules in the way that they're responding to these in the human system. So now what can you do, right? So in another setup, we actually made a so-called foreign body on chip response device, which is using a same baseline kind of chip design, having the bottom chamber, having the endothelial barrier, and then having the top vascular chamber. So then what's now happening here is that you can start to circulate these monocytes on the top layer of the vascular chamber and look at how these immune cells interacting with endothelial barrier and also the other things down in the tissue chamber. So if you don't have any flow in there, don't really see any activation of the monocytes in there, but if you have the dynamic culture, you can start to see some of the activations of the monocytes or immune cells on this endothelial barrier, right? So red color shown here. But now if you start to have your foreign body kind of implant in this bottom kind of chamber here, you can start to also look at how these immune cells are migrating through this endothelial barrier and then start to interact with this foreign body kind of implants in the bottom tissue chamber, right? So these are basically the titanium microparticles that are put in there as implant. But what's interesting here is that if you have these immune cell, same implants, the same titanium beads, but if you have the donor immune cells coming from 3 different donors, you can actually see a spectrum difference depending on where the cells is coming from, right? So for example, donor B and donor C, well, not really much inflammation going on there with this like microbeads, but then for donor A, you actually see much stronger inflammatory responses of their immune cells towards these implants, meaning that you can use this device as a very simple kind of in vitro platform to really like allow a screening of like foreign body responses before you actually put the material into human like individual patients. All right, so another simple example is we have been using this like multi-compartmentalized devices to look at cancer metastasis. So what happens here is that you have a liver chamber, for example, on the left that's based on JAMA hydrogel, but on the right you have a bone-like chamber that's containing either pure JAMA or JAMA plus this bone mineral hydroxyapatite. So this is more mimicking the bone microenvironment, and you can see with this configuration, you can have much more migration of the or metastasis of the liver cancer cells into the secondary kind of bone site. And with that setup, you can also start to flow in all the kind of particles or drug molecules in there to look at their responses. Right? If you have free drug, you can have some suppressing kind of effect, not too lasting. But if you have the drug that's encapsulated into the nanoparticle, then you have much more sustained responses of these inhibition effects, right? So you can see much fewer number of cells going into secondary kind of site, meaning that you can suppress these metastasis of primary liver cancer cells. All right. So then, as mentioned, you can also start to look at mechanical actuation on the cells, right? So what happened here is that we build a little kind of, again, compartmentalized device, but now the membrane is actually elastic. You can start to stretch these cells on top by applying a vacuum pressure at the bottom, right? Depending on how large the vacuum pressure is, you can actually have different strain levels applied to these cells. For example, 10%, like 10 kilopascal, you're having probably around 9% of strain, which is physiological. But if you increase that to 20 kilopascal, then that's becoming 16%. That's becoming more like pathological or hypertensive kind of strain level. So depending on how large the strain that you place on these cells, these are actually smooth muscle cells cultured on this membrane, you can start to look at their responses, right? So if you don't have any strain or only have physiological strain, you don't really see much of the inflammation. But if you start to do 16% strain, which is pathological, you can start to see pronounced inflammatory responses by these smooth muscle cells on top of the membrane in the way that's very similar to when you induce the inflammation using a chemical, which we know very well that's inducing their inflammation, right? So indicating that, I mean, by simply applying these mechanical kind of cues, you can start to move the cells into some inflammatory phenotypes similar to when you apply some chemicals that are doing that. So meaning the mechanical actuation is actually becoming very important in these in vitro kind of organ-on-chip devices for modeling some of their functions and also disease phenotypes. All right, so another example, more recent example is that, I mean, conventionally, I mean, these devices, you have to really make them in the clean room and assemble them together. So, I mean, the process is kind of labor intensive and potential time consuming, right? For making a single device, a single device might be okay, but if you want to make many copies of them, it might be problematic if you want to achieve a certain complexity. But now, recently, we have been working with our collaborator at the Northeastern, Dr. Livermore. So I've been using these like origami approaches to really pre-pattern these kind of strips or kind of like flattened devices. And once you want to make devices, just simply fold them into the shape that you want, and eventually you can have a three-dimensional chip device that's having all the complexity that's involved in these different layers of chambers and stuff, right? So one of the examples, we have made the like endothelialized, the liver-on-chip device, and you can actually see very nice population of these hepatocytes or these endothelial cells on the different compartments, and mimicking this like liver lobule sinusoidal kind of compartmentalization sort of structure in vitro. All right, so then coming back to a little about the bioprinting, biofabrication. So as we know, I mean, the human organs and tissues are complex, and these are their corresponding micro-scale tissue building units here shown. And everything here is also complex, having multiple cell types coming together, having multiple ECM types coming together in the right architecture in order for the macro-scale tissues to be functional. So the challenges here are really how to mimic the complexity of native tissue microarchitecture and how to reproduce the synergistic interactions of the multiple cell types. So with that in mind, I mean, there have been many conventional kind of biofabrication approaches, for example, based on pro scaffolds or whatever stuff. But then issues with those that the are usually based on manual or semi-manual operations. So meaning that if you're trying to make one copy, that's okay. If you want to make tens or hundreds of copies, that can be labor intensive, and also reproducibility is going to be low, right? So that's why in the past 10, 15 years, people have probably more 10 years-ish, people have been really trying to work on these bioprinting methods to allow really automated control of patterning of cells and ECM molecules in a nice spatial way, right? So then with that in mind, we have been really working on many different aspects, essentially any aspect of bioprinting, ranging from hardware, software engineering to biomaterials and all the way to downstream applications. Some examples shown here, for example, we have been really into this multi-material bioprinting because, again, capacity to really print multiple materials into these tissue constructs, that's becoming very important. We have also been working extensively on this Canon tissue bioprinting, basically bioprinting of the hollow tissues that are widely present in human system, right? So like the vessels or the other kind of hollow tissues. And also we have been working on these bioink developments. As mentioned, bioinks are probably one of the most important components of bioprinting that not only have to ensure that the printing is happening in the first place, but also after printing, they have to ensure that cells are growing there, functioning there, in order to have the final mature tissue to be built. So that's also become very important. And that's thing that we have been trying to have these minimally invasive bioprinting methods developed as well. So basically combination of the conventional bioprinting methods with more modern sort of surgical equipment, or you can make them in a way that you can hold them in hand so that you can start to really print these direct on the wounds in situ without having to print them in an implant, right? So I'm going to give some examples, not too many today, primarily on multi-material bioprinting and moving to some combination strategies towards the end. So as mentioned, multi-material bioprinting, that's become very important. So this is an example of multi-material extrusion bioprinting. So what happens here is that we actually combined the outlets of the different bioinks into a single nozzle. So it's multi-channel but single nozzle platform. So why is that important? So in this case, if you want to switch a material, as you can see from this movie, you don't have to switch your nozzles, right? In the conventional sense, you have to, if you have a multi kind of nozzle platform, you have to physically switch nozzle. We'll try to switch a different material. So in this case, everything's coming from same nozzle, so you can actually save a lot of time because you don't have to change the nozzle anymore. So you can start to print very complex structures like the heart, whatever things as you want. Right, so that's multi-material extrusion bioprinting. So these are having more interfiber heterogeneity, meaning that the heterogeneity or multi-material is between among the different fibers that you deposit. But how do you actually induce interfiber heterogeneity? So working with some of our colleagues in Multitech, we have really been developing a way called continuous chaotic bioprinting, basically using this chaotic mixer that's been long used in chemical engineering, and allow infusion of these different bioinks into this mixer, and eventually after passing through these elements in there, and depending on how many elements you have, you can start to have this intrafiber heterogeneity build up over time, right? So as you have more and more elements, you have finer and finer striations that's happening in there with this multi-material kind of chaotic bioprinting platform. So then those are based on extrusion bioprinting still, but then you may wonder, how do you make more complex structures with multi-material capacity, right? So this is actually something we have been really more into recently. So this is so-called digital light processing based bioprinting, which is very different than the extrusion bioprinting. So what happens here is that you have a little reservoir here that's infused with the liquid bioink that's photoactive. So if you shine a pattern of light at the bottom, it's going to pattern a layer of the liquid or the ink into a solid structure, and you can move the stage up a little bit, right? So then you can basically pattern another layer at the bottom. So if you move, do this again and again repeatedly, you can eventually imagine, right? So you can form a complex three-dimensional structure that's volumetrically sophisticated, right? So then that's allowing to really print something that's more complex. But then the issue with that is in the conventional sense like this, right? So you only have a single reservoir, which means that you can only print single material at a time. So having some efforts on multi-vat based printing, meaning that you have multiple vats, but they have to physically move your things across to be able to really print things that's multi-material. That can be very labor intensive as well in this case. So a couple of years ago, we have been really developing a way to streamline this process by integrating a microfluidic device into this reservoir platform, right? So here what happens is that now since you have a microfluidic chip device in there, you can start to automatically infuse this different bioinks into this reservoir area and allow like fast DLP-based layer by layer bioprinting to happen in the place, right? So that gives you the chance to really get more faster printing of multiple materials into these complex tissues very nicely. So more recently, we have further built a mixer device into this device, into this microfluidic chip device. So now you can start to also really pattern more complex or finer gradients into this three-dimensional structure in 2 dimensions and 3 dimensions as well. All right, so in the last maybe 5-10 minutes, I'm going to briefly discuss about one of our recent works on really combining these different technologies, right? So again, I mean, we have been really trying to, as mentioned, combine the different technologies because each of them has their own advantages and disadvantages. For example, by printing, you can get very complex structures built, but then if you want to have them placed in a dynamic microenvironment, that's becoming sometimes problematic. On the other side, if you have the chip devices, I mean, they can allow very nice microenvironmental control, but oftentimes they're compartmentalized, but they're not really three-dimensional in essence, right? So really, you have to really try to combine these different technologies in a way that we can form high content, physiologically relevant human tissue models in vitro, not necessarily by printing, but by fabrication plus the on-chip configurations. So one example is you can actually form this spheroid of livers and then basically print them into these bioreactors. So this is one of simplest forms, and from there you can start to really test drug molecules in a dose and time dependent effect, right? So these are molecules that were initially in the market and then basically got recalled because of liver toxicity that was not initially observed in the screening process. So we actually use this platform to really look at how they're responding to these like liver toxic molecules in a dose and time dependent configuration. So then that's more spheroid-based structure, but then you don't really have any like liver-like lobule structure in there, right? So then if you use a DLP or for the pattern technique that I just mentioned, you can start to also pattern these liver lobule-like structure in the way that's very similar to the in vivo structure, right? So this on the left is monoculture, having only hepatocytes in there. The cells are growing pretty nicely over days and maintaining viability. And on the right, we show that you can also do co-culture. For example, you can not only pattern the liver cells, but you can also pattern liver cells plus the stellar cells in there. So after culture, what's happening is that while the liver cells more staying within the lobules, the stellar cells will actually migrating more into the surrounding kind of sinusoids. That's actually very similar to the in vivo configuration. So you can use these models to really better mimic the like in vivo structure of the liver. So then you can have their all functionality, right? So affecting staining and also cytochrome. So basically expressing pretty nice cytochromes with this configuration, like the lobule kind of patterns. That's very much mimicking the in vivo configuration. So then you can one thing we have been partnering with our colleagues at Mayo to use these models for more tests like safety screening for COVID drug candidates in the past couple of years. I'm going to skip this couple of slides. And then the other thing that why you see that those kind of models are lobule-like, it's still lacking vasculature. So you may wonder if you want to build vasculature in there, how do you do that, right? So another possibility is that you can use another more complex bioprinting method, sacrificial bioprinting, to create microchannels within this liver-like constructs, right? So what happens here is that you print a template that can be eventually removed away to create a channel in there. So now you can start to not only have the surrounding matrix containing liver cells, but also you can endothelialize this this microchannel that's hollow perfusible, right? So it's becoming an endothelialized or vascularized liver construct. So from there, you can start to infuse your drug molecule through this endothelialized like vasculature, and not only can you see how the drug is breaching endothelial barrier integrity, but also how the drug molecule is also exerting its toxicity effect on the surrounding liver cells in a time, dose, and more importantly, diffusion dependent manner, right, as you can see from here. So that's actually becoming very important, because in the conventional setup, if you have a two-dimensional static cell culture, then if you put a drug molecule in there, then every single cell is going to experience the same dose at the same time, which is not physiological at all, right? So in the human system, if you have a drug in there, it's going to be carried through the bloodstream in most cases, and then to the tissues, and depending on how far away the tissue cells are from the vasculature, there's going to be diffusion dependent effect. So that kind of thing can only be modeled in this sort of like more complex human tissue models in vitro, right? So that's becoming very important for modeling purpose. All right, so last maybe 5 minutes, I'm going to really talk about another sort of combination. So not only not really bioprinting here, but it's more conventional biofabrication to model a distal lung on a chip in vitro. So people are probably very familiar with this Emulation chip devices, right? So basically, they have a flat surface that's modeling a lot of tissues, including the lung. But then the issue with that is sometimes when it's a lung model, or specifically when they're caught a alveolar lung model, they're not really structurally, right, because it's still flat surface. If you look at the actual structure of the distal lung, human distal lung, you have all those kind of sacs that are connected together in a way that they can be expanded and shrunken depending on the breathing movement, right? So that's becoming very important for a lot of things, and this is something that we have been really trying to model in the past years. So the approach that we have been trying to do that is developing these so-called inverse opal scaffolds, also based on the templating approach. So what happens here is that you have these microparticles based on alginate initially made and packed together in a way that they're close packed. And then in between them, you can actually infill the gelatin methacrylate solution, right? Basically JAMA solution in there. And then after you cross-link the JAMA solution, you're going to form a scaffolding system in between these particles, and you can selectively remove these alginate microparticles as templates, and then you can start to have the hollow spaces like the sacs that are built in between the different within the scaffold, and between the sacs, you can also have the interconnections that allow gas exchange in there, as you're showing this SEM image, right? So then, if you see these alveolar epithelial cells in there, you can see very nice population of these epithelial cells on the surfaces of these sac-like structures. And here's confocal showing that, and we can also see the interconnections in between the sacs, and they are expressing nice biomarkers like ZO1, the junction proteins. You can, if you do a cross section, you can also see very nice monolayer kind of configuration of the cells on top, right? So the cells are maintaining their viability over there as a culture as well at pretty high value. So why is that important? I'm not going to go any detail into this, but message here is that, I mean, if you compare, for example, three-dimensional JAMA configuration, which is in our case, to not only two-dimensional JAMA, but also two-dimensional PDMS configuration, which is being used in many of the conventional kind of lung-on-chip devices, you can see a lot of differences in there. So take-home message here is really, I mean, it's not only the structure that matters, but also it's a mechanical property of the matrix substrate that matters as well, right? So a lot of parameters, it's often a combination of these parameters that are determining how the cell is going to be responding to this microenvironment. And our three-dimensional gel-based microenvironment is actually much more physiologically relevant than some of the other conventional models. So then, as mentioned, you can start to combine that with a chip device, right? So if you put that into a chip device, you can start to not only perfuse the bottom of the like lung sort of model, but also you can start to mechanically actuate them, right? So you can actually allow them to breathe. This is one breath every 3 seconds. That's physiological, and then it's like 10% of strength, which is also physiological. And with breathing, you can see nothing is changing to these cells. I mean, they're still alive, but also, but instead, you can actually see much better expression of these biomarkers, junction biomarkers in between the cells. Right. So then you can then subject them to different testing. So another thing I have to mention before I end is, I mean, this is actually becoming very important, because if you have the conventional flat surface-based model, even if you can breathe them, the air trajectories in there is very random, which is not physiological at all. But if you have our device, right, three-dimensional kind of scaffolding system in the chip, you can brace them. The edge trajectories are becoming much more physiologically relevant because, I mean, when the air or particles come in, they actually hit the wall, and then depending on where they are, they can sometimes also kind of go through this windows connecting the different kind of sacs. So that's very important because, I mean, there's a layer dependent effect, right? So depending on how close these sacs are with the inlet, there's going to be many different air kind of flow, like trajectory changes in there. That's not possible with conventional flat surfaces. Right, so with that in mind, we can either do smoking tests. For example, we can smoke device with like cigarettes, and then look at how the cells are becoming dead, and how the membranes are getting oxidized, and how their biomarker secretions are all changing. And we have also basically done a little sort of initial SARS-CoV-2 pseudoviral kind of infection assay. The cells are expressing all the nice biomarker like ACE2, as we all know. And if you subject them to SARS-CoV-2 pseudoviral kind of infection, you can see how the viral particles labeled in red here are actually infecting the cells, but at the same time how the epithelial cells are kind of dying out without any drug treatment. But if you have this drug infused in there, you can start to see much better viability of the cells, right? And what's interesting here is that we actually showed very practical kind of clinical relevancy, because hydroxychloroquine, for example, we know that it was initially used for COVID treatment, but then got off the market because it was shown not to be very effective, which is also shown in our case, right? So if you look at this hydroxychloroquine treatment here, it's not really effective. But remdesivir and some other drugs are becoming much more effective than hydroxychloroquine tested here. So meaning that these models are potentially translational as well to really predict how the drugs are going to affect our patients in real life. All right, so I think from there, I'm going to really end by one slide showing that we have also been doing some like sensing work to allow in situ real-time calculations of these microtissues in the microfluidic devices. And from there, I'm going to really thank all the wonderful collaborators and our funding agency, and of course, all the wonderful lab members that have done pretty much everything that I have presented today. Thank you very much.
Thank you for your presentation. Unfortunately, we don't have time to the questions, and the organization will send you the question. Thank you very much.
All right, thank you.